Welcome back, everybody, to the final 3 sessions in our engineering track here at F8. We have, coming up after this, a data infrastructure session, which is going to be amazing. And we're going to finish off with developer infrastructure at 4:30, and I promise you do not want to miss that one. So basically what I'm saying, you need to stay here for the rest of the afternoon. But we're going to start off with a topic that is near and dear to every engineer at Facebook's heart. As I'm sure you know, our motto for a while was move fast and break things. Well, it turns out the trick is to move fast and not break things. Performance remains extremely important for us across our entire family of mobile apps. And to talk more about how we do that and how we ensure that they stay fast, I'd like to introduce the team, starting with Subbu. Come on up.
Thank you, James. Can you guys hear me? It's a clicker. Thank you. All right, guys. My name is Subbu Subramanian, and I lead the performance efforts at Facebook. Most of you know why performance is important for any product. However, there are a few key reasons why it's particularly crucial for Facebook. In this session, I wanted to share with you some of those reasons, a lot of the challenges that we face in making our applications extremely fast, and hopefully some of those learnings that we have gotten, the best practices, tools, and even some code that may be even useful for you as you build your own apps. Thank you for attending this session today, and I hope you will find this valuable. As you may have heard in the previous sessions, Facebook has been growing rapidly in a lot of the emerging markets in developing countries. In these countries, many people use Facebook solely as a means to keep in touch with their friends and family and loved ones. This is not very different than what happens here in the USA. We also use Facebook to keep in touch with our friends and family. But there are a couple of key things that are different about these markets that are very unique to them and unlike what happens here. People use a wide variety of devices, ranging from low-end 64-meg single CPU phones to octa-core devices that are the yesteryear supercomputers. And these devices also run a variety of operating systems, especially on the Android ecosystem, anywhere from Gingerbread all the way to Lollipop. And they remain in various versions, and some of them upgrade, some of them don't. And it's like a pretty complex ecosystem of devices and operating systems that are being used in these developing countries. Second, they access Facebook via a variety of different networks, from 2G to modem to occasionally Wi-Fi or LTE. Even when they are on Wi-Fi, the network accessibility and the quality is extremely variable. Ensuring the Facebook app is consistently fast and responsive in the midst of this particular ecosystem is a huge challenge for us. What is worse is the experience of our own developers, like you and I, that hardly mirrors what I talked about earlier. Most developers live in ecosystems like Silicon Valley, where we have great phones, high-end phones, amazing resourcing power on the devices. And we are also mostly on LTE and Wi-Fi networks that are fairly fast. This makes us completely oblivious to a lot of the challenges that we face in the developing markets that I just outlined. And it makes it hard for the developers to internalize and empathize with these users and really figure out what the challenges that they have are and how to kind of tackle them. In short, the developer world does not reflect the realities of the developing world. So what did we do? This is what I was talking about in terms of the various networks and the phones that we use here, which are pretty much homogeneous and have a really nice network capabilities. So what did we do? A couple of years ago, we sent a bunch of our developers to understand and internalize these challenges on the ground in these markets. We sent them to Africa, Asia, and Mexico. In the previous sessions, for those of you who were here, they must have heard some other stories about how a team went to India and experimented with all the challenges there. So I'm going to quickly summarize what happened in the visits that these engineers made to some of these countries and what they learned from there. Some engineers went to Kenya and were told that performance of our app is highly variable based on network and device conditions and operating systems they run. Engineers who went to Nigeria, on their way to the airport, on the way from the airport to their hotels, they stopped by a kiosk to buy this 30 MB pay-as-you-go SIM card. That's basically the pay-as-you-go data card. That's the most popular there. And then they started using Facebook, and then they found, to their surprise, that they exhausted it like much sooner than they had anticipated. What is the team that went to Mexico here? That, especially on Android low-end devices, the application starts up really slow and also consumes a lot of battery. By the way, I come from India, and this is personal for me here in India, where every time I go there, like my friends and family complain to me about how slow the app is, reminding me of work that I need to get done while I'm on vacation. So the developers came back, resolving to fix these issues as soon as possible. At Facebook, we rely on deep data analysis to drive a lot of the decisions we make. One such analysis showed that as people upgraded from low-end devices to high-end devices, the usage of Facebook and the general experience people have went dramatically up. What was fascinating about this was that a lot of the perception of user experience benefits that they got came from the app speed increase they got from upgrading to better devices and better hardware. So in some sense, the improvement in performance was a huge factor in their experience of Facebook as a product. So we kind of got very curious about this, and to ensure that this was indeed the case, we drove much deeper into the data and looked at every interaction to see what it was, whether those had specific impact across those interactions and products. And the deeper analysis on interactions like comments, likes, photos, and across all of this, the total user experience was indeed quite correlated with improvement in the performance of the devices. So our analysis was pretty conclusive. Almost every interaction beyond all these things I've listed here got a boost. Bottom line is that performance drives user experience, and our data science proves it. And this is true across the world, because there's tons of data from every country, every continent. So we talked about a couple of challenges earlier as we kind of tackle these realities on the ground. One of them is the massive worldwide growth and the diverse devices and network conditions. There are a few other challenges we had to tackle on our way to improving the performance of our apps. As you may have heard in other sessions, we strive to launch our applications quickly and often. Our main Android and iOS apps get released every 2 weeks to the Google Play Store and iOS Store, respectively. And we have a number of other independent apps that keep getting launched very often. Ensuring the app performance doesn't degrade in the context of this high code velocity, and making sure that all of a performance bar is met as the code gets shipped is an extremely big challenge. The product engineering teams at Facebook, Product engineering teams at Facebook also have great autonomy. They almost act like independent startups within the larger ecosystem. And ensuring they all adhere to the common standards, performance guidelines, tools, and the methodologies that we have to ensure that all apps are fast requires a lot of innovative technical as well as management or organizational solutions. So how does performance team ensure that our app is highly responsive, very reliable, and use the least amount of resources to provide a delightful experience to our people? Marty Greeny, our iOS performance engineer, will answer some of these questions in the context of what we did on iOS. Over to you, Marty.
All right. Thanks, Subbu. Good afternoon, everyone. My name is Marty Greenya, and I'm an engineer on the mobile performance team at Facebook. And I want to talk today a little bit about improving performance on iOS. You've heard from Subbu, there's a lot of benefits that we know that come along with improving performance on various user interactions and user experiences all through the app. And when we've identified that there is a problem and an opportunity, we really want to get in there and improve things and make them as fast as possible. So when we've identified that there's an opportunity, there are 3 major steps that we go through to make the app as fast as possible. The first is investigation. We collect a bunch of data, we create a story of what's happening, we identify the main technical levers that'll get us to our goal. Next comes the engineering execution. This can be simple things like maybe refactoring code or classes, but can also be more complicated things that involve creativity or innovation. And lastly, we've worked hard to get our performance wins. We don't want regressions sneaking into the build and eroding all of that progress. So I want to talk a little bit in detail about these 3 steps. And to do that, I'm going to use an example, application start. About a year ago, we decided that application start really wasn't where we wanted to be as a company. And for those of you who don't know what application start is, this is the situation where you've got your phone, you want to see your feed or see your friends' apps, or friends' pictures. You tap on that icon on the main screen. You get a splash screen come up, your content starts to load, and then you're left here staring at a spinner. It goes on for 5, 10 seconds, sometimes maybe even longer. And all you can think about is, where's my content? And this is pretty much where we were about a year ago. And this is what we wanted to make better. So the first step in this process of our investigation was data collection. There are 3 major sources that we get data from here at Facebook. The first is on-device profiling. Most of you on iOS are probably familiar with Apple's instruments. And this is actually an extremely powerful tool for profiling a single device, figuring out all the low-level operations going on in the phone. At Facebook, we also have the fortune of having a device lab that lets us run tests multiple times over and over again, a single test, and collect data, aggregate results, and basically take the variance out of a single interaction. And then lastly, of course, we have production metrics. This is the data that we get from the users out in the field that literally tells us exactly how long application startup is taking throughout the app, throughout all of our user base. So this kind of gives us a spectrum where we've got, on the one end, sort of really high resolution, high detailed data. On the other end, we have truly representative, truly accurate user experience. And we want to be able to gather all of this data and synthesize a story of what's going on in our users. So let me dig in a little bit into detail for these. So profiling, again, using Apple's instruments. This is only going to be a single app running on a single phone. Simply, that's because how instruments works. But we can still get a lot of really useful data. CPU, disk I/O, network I/O. When we started looking into these metrics, focusing on disk I/O, we actually saw that core data was a major source of I/O in our application start. This was one of the first bits of evidence that motivated us to move off of core data and onto our own system. Next was network I/O. When we traced network I/O during application startup, we actually found a ton of network requests that no one really realized were going out. And it was really straightforward to just prioritize those to only focusing on the ones that were blocking for the user experience, and then delete all the others for later on. So next, we looked at lab testing. Here we have a device in a device lab running the same test over and over and over again, maybe 10, 20, 30 times. This lets us automate data collection and also see aggregate analysis. So you can see in the example here, we've got some top modules highlighted, how long in terms of CPU they're taking to run during app startup, and the variance that is within those particular code paths. This is a really nice way of kind of dialing in on specific modules and code and seeing it improve as we check changes in. And last is production analytics. These, in some ways, are kind of the gold standard. This is the metric that we're trying to move, because this is literally what our users are seeing out in the field. This is real devices on real networks hitting real servers. And we can measure all of that in real time from Facebook and slice and dice the data to see, well, which devices are performing the worst, which networks have the most trouble. This helps us focus our engineering effort only on the opportunities where we think will make the biggest impact or where things are performing the worst. So this is great. We've got a ton of data coming in. We're starting to create a story of what's happening inside the app. As you can see here on this chart, we've got all of the CPU data from various profiling and tracing runs put onto a single pie chart. So as we started to attribute this runtime of the submodules, we pretty quickly realized if we wanted to make an impact, we can't be focusing on this long tail of ones and twos. We need to be focusing on these big chunks of the pie. When we did this, we saw, for example, that our memory caching and core data layers were actually taking a pretty substantial amount of time in CPU. You might have heard in previous talks that we eventually moved off of core data and onto our own system, which we called mem models. And this was a pretty big CPU win. Likewise, we found that our view model layer wasn't quite where we wanted it to be in terms of CPU, being another bit of evidence that motivated us to the component system, which, as you heard yesterday, we've now opened up. So we understand these major technical levers, and in CPU land, at least, we've started to really cut down on what was going on. And after some work, we were in a pretty good shape for CPU. But there was another problem that was really hurting our application startup, and that was the network. So that brings me to my next topic, which is request priming. Really, the problem here is that networks are slow. Even on a high-quality network here in Silicon Valley, maybe a 3G or a LTE network, it's not uncommon to get 400 milliseconds of latency from a client to a server. This is really rough for connection establishment time, where on top of your TCP connection establishment, you might have TLS SSL to keep things secure, which can add 3 round trips to the server before you've even started making requests and downloading content over a second. In addition to that, there was a large number of things that had to happen, both on the client and the server, in terms of initializing subsystems and handling request processing. And that was all naively, of course, being handled sequentially. So let me illustrate just precisely how things were when we started. So the user taps the icon on their main screen. The client does all of its local initialization of subsystems, sends the request up to the server. The server handles the request, processes the response. Response goes back down to the client. Finally, we can show the client, the user, the stories that he wants to see. In the world of request priming, we've moved to a system like this. As soon as the application starts up, we send a priming request up to the server. Now, both the client and the server can run in parallel. When the client is done, it sends a proper request to the server, which immediately serves from cache, and we're able to show stories and content much faster to the user waiting on the client side. So in theory, this sounds really great. In practice, there was quite a few challenges that we had to overcome in order to make this happen. The first was security. Of course, we didn't want to open ourselves up to any kind of attack, either on the client or on the server. So we worked with the security team to make sure that both of our endpoints were hardened. Next was privacy. At Facebook, we really respect the privacy of our users, and we wanted to make sure that no personally identifiable information was transmitted over the wire in plain text, where it could be intercepted or otherwise snooped on. So we made sure the whole solution had industry-strength encryption from top to bottom. And then finally, performance. Performance is the goal of all of this. We don't want to spend a ton of time generating a request query at the beginning of application startup. So we came up with a pretty simple but actually really effective solution to simply generate the request required during application start before we exited the app on the previous run. When the user starts up the app, we simply have to basically stream a buffer out over a socket, and we're good to go. So this is great. We built our rocket ship, we're ready to go. All the internal validation is looking pretty good, but you never quite know until you put it into production. So we shipped it, and a few days later, when we got the data, we were seeing over 800 milliseconds across all devices off of our cold start path. So this is amazing. We're super excited. Finally, we're making a big impact in our cold start. But even as we're sitting around patting ourselves on the back, there's one fear that's creeping up behind us, and that is regressions. What if someone checks something into the code that regresses us and undoes all this hard work that we made? So to prevent regressions, we developed CT-Scan. CT-Scan is an automated performance regression tracking framework. And essentially what it does is runs performance tests on devices constantly, all day long. It'll start up the app, measure how long it takes to reach conclusion, measure that time, record it, kill the app, and start over again, just constantly all day long. This gives us a really good heartbeat on how our code is performing, even on a day-by-day basis, hour by hour. To do this, of course, you need a lot of devices, which is where Device Lab comes in. This kind of looks like a showroom from like an AT&T, but this is actually the Device Lab we have in Menlo Park. And this is from circa about middle of last year. The CT-Scan project originally started off essentially as a phone on one guy's desk. But the value was so great that we kept growing bigger and bigger and bigger until we had rooms full of these devices. But the value was still there, and the value was still growing. Which brings us to today. We've actually designed our own custom rack. We're filling these racks top to bottom with iOS and Android devices that are going to be running performance regression tests all day long, constantly. And we're going to be filling up our data centers with these to give us the capacity that we need to do the regression testing that we need to keep the quality high in our application. So this is great. We've got the CT scan framework. We've got the devices that we need, the capacity. What does this look like as an engineer at Facebook? So let's say you've got a feature, something you're working on. You're in development mode. Hopefully, you don't want to regress things, so you want to maybe check it out. Or even better, maybe this is a performance optimization that you need to test. You can manually, at this point, voluntarily submit it to CT scan. And within a couple hours, you'll get feedback, whether things have gotten better or hopefully not gotten worse. Let's say things have gotten better. So you commit to master. At this stage, CT scan has a cadence in which it pulls builds from master and runs performance regression testing on the whole branch. Let's say at this stage, nothing has gone wrong, performance is still looking good, we can release it to production. And here's where those performance analytics from the field come into play. We can get this data, compare it against what we're expecting from our in-lab testing, and see if things are panning out the way we're expecting them to. This is great. As an engineer, you have a safety net now. But what does it look like in practice? So here's a block of code. This is the before. An engineer checked in a diff, which you can see here. And CT scan flagged this second block of code as a regression. And I want to give you all just a few seconds to kind of look at this and see if you can pick out which line caused the regression here. So you can see pretty quickly, instead of using the IVAR, we're actually using the self.dot syntax to access the variable. So you might think, OK, is this maybe some kind of a clowny setter and getter? Maybe we have something custom going on. The engineers dug in, and actually that wasn't the case. So that's strange. Now what's going on? Digging a little bit more, we found there was an unrelated KVO observer in a completely unrelated block of code that was using the original target setter to kick off a massive amount of work. And this basically one or two lines was causing 700 milliseconds of regression in this particular interaction, which is crazy when you think about it. All these engineers spent months working on request priming. That got us 800 milliseconds. A single line of code sneaking into the build can take 700 milliseconds away from us. Fortunately, CT scan was here, and this was reverted. So hopefully this kind of gives you an idea of the steps that we go through at Facebook, investigating, executing on the engineering, and then using regression testing to make sure things don't sneak into the build. And with all of this together, over the past 6 months, we were able to get application startup cut in half across all of our major devices on iOS. This was essentially like giving a device upgrade to all of our users. And who wouldn't want a device upgrade? So hopefully this was interesting for you. And up next is Florian to talk about image performance on Android. Here you go. Thanks.
Hi. So my name is Florian LaPlantif, and I'm an engineering manager here at Facebook working on Android performance. And today, I want to talk to you about Android image performance. So if you're building an app on Android today, it's pretty clear that you have to have great image performance when it comes to loading, fetching, and caching images. Facebook's own flagship applications make heavy use of images in all of their key features, be it from the main Facebook application with newsfeed and sharing photos with your friends, to Messenger and direct sending of photos or animated stickers, that's my favorite, to Instagram, which is an application entirely built around the concept of sharing rich visual content with your friends. However, building an app on Android that deals with photos in a performance way is really hard. So by now, if you've attended all our talks, you know that the networks on mobile are flaky. And what that means is the network is either unreliable, it comes up, it comes down, you can't trust it. It's just kind of a fact of life that you have to deal with. Particularly with images, this is really hard to do. When it comes to disk and memory, you have to be very careful. You don't have an unlimited amount of disk space that you can take up for your application. And memory, particularly on Android, for low-end phones, is really limited for your application. So when it comes to loading large bitmaps into memory, again, you have to take care not to mess it up. Obviously, I'm part of the performance team, so I like fast things. So whatever solution you build, it has to be fast, and it can't have any performance bottlenecks. You have to be able to deal with many formats, from the more common TNG, JPEG, to more exotic ones, maybe like animated GIFs or animated WebP. And in order to connect the entire world, we have to make this work all the way back to old versions of the platform, namely Gingerbread. So we weren't quite happy with the state of image loading in our applications, and we looked at what the existing code was, and frankly, it was kind of slow, bloated. It was going to be really hard to refactor, so we knew we had to do something else. We looked at open source solutions first. We really like open source at Facebook, both contributing to it and using it. But sadly for us, and there's great image loading libraries on Android, but sadly at the time, there was no image loading library that did everything we needed all the way back to Gingerbread. At this point, a small team of determined engineers from the Facebook London office decided to set about working on what would an image loading library for us look like for Facebook. This image loading library obviously should be very good about managing memory. You can very easily shoot yourself in the foot if you allocate too many objects on Android because you pay the garbage collector cost. And also, when you're dealing with large images, it'd be preferable to have all of that memory be on the native heap if you could do it. You'd have to improve scrolling performance and not degrade it, and this is really hard. And you'd have to be aware of when images are loading into the viewport, loading out of the viewport. You'd have to deal with caching and fetching. We talked about hard problems with the network. They're unreliable. And you can't just make optimizations. At some point, you also have to provide features for your users to deal with these bad network conditions. You'd have to support all the image formats that we talked about, as well as all the image sizes that you cared about, and resizing of images if they were too large when you downloaded them, and doing that in an efficient way without blocking the UI thread. And finally, you'd have to do all of this all the way back to Gingerbread. So obviously, when the team started out, this was a hard problem, and it didn't take them just a week to fix it. But after several months of hard work, they had come up with exactly a library that did all of this. And they called it Fresco. And in order to tell you more about Fresco, I'd like to invite one of the engineers from the Facebook London Android team, Ogi.
Hello, everyone. My name is Ogi. I'm part of the Android Prod infrastructure team in Facebook London, and I'm going to talk about Fresco, our new imaging library for Android. Fresco actually consists of two parts. The first part is image pipeline, which is in charge of providing an image, and the second part is Drawee, which is responsible for displaying that image. Both of those parts are executed on your Android device, so those are purely client-side libraries. Before I dive more into Fresco, let me tell you about some of the history behind it. We're seeing many out-of-memory errors, and we wanted to reduce them. Furthermore, when garbage collection happens, the system has to pause the app for a brief period of time, but still long enough to cause stutters while scrolling. We obviously wanted to avoid allocations and garbage collections as much as possible. So we moved practically all of our images to the native heap, but there was a catch with that. To keep the images on the native heap, Android provides purgeable bitmaps, and the problem with them is purging itself. Namely, purgeable bitmaps, unless pinned, can be reclaimed by system at any time, and if that happens, those images will have to be decoded again the next time they get pinned. What's worse is that this decode happens on the UI thread. To avoid that, we keep all of our bitmaps pinned at all times, and once we don't need them anymore, we recycle them manually. What that basically means is that we are dealing with deterministic memory management. As Florian mentioned earlier, we looked into some of the existing libraries, but none of them really provided a solution to all of those problems. And since adapting those libraries would be fairly involving, we decided to build our own. So, what is it that our library has to do? Well, it has to fetch the image, being a network or a local file. It has to cache the image on disk and in memory. It has to decode the image, of course. But we might also need to resize or rotate the image in case the image is too big or if the orientation has to be corrected. And finally, we might even need to transcode the image in case the image format is not natively supported by the platform, such as WebP prior to Jelly Bean. But this is not all that our pipeline needs to support. It supports animated GIFs and animated WebPs. It supports progressive JPEGs so that the image can load progressively rather than having to wait to be fully downloaded. We support post-processing. Blur would be one example. Then there is instrumentation, and this is very important for identifying areas for improvement and also for regression detection. And finally, there is a support for cancellation, prioritization, and prefetching. So to display an image provided by the pipeline, we use Drawee, and I'll talk about it in a moment. And to prefetch the image or to do something else with it other than displaying it, we can do it as follows. First off, we need to build an image request. That can be as simple as just specifying the URI, but there are many other options available. Then, if we say I want to prefetch the image, we just submit that request as a prefetch, and we are done. If we say we want to fetch the image only if it's in the bitmap cache, we submit that request, and the pipeline returns a data source. Data source is much like Java future, except that it can provide multiple results rather than just one. So here we get the image from the data source, and then we save it to a temporary file. One thing to note here is that since our image pipeline requires deterministic memory management, we need to be careful to properly release the resources once we are done with them. Hence those try finally blocks with close. So we built our pipeline, but as you can see, using it is fairly complicated. And at that point, I knew that we need to provide something to simplify this. So I locked myself in a room. I spent a couple of days thinking about how to solve this particular problem. And eventually, I came up with something that we now call Drawee. The good news is, with Drawee, we don't have to do any of this to display an image. And this is one of the reasons why we built Drawee. The other reason was to provide a commonly used functionality rather than having developers reinventing the wheel over and over again. And finally, we wanted to reduce the memory footprint of our view hierarchy. There are a couple of things that Drawee does. It submits image requests as required. It releases the resources once they're not needed anymore. It tracks the view's visibility in order to tell when to submit and when to release. It can handle some gestures, such as stop to retry in case the image load fails. And finally, displays the hierarchy, which I'll explain in a moment. There are three main components in Drawee: the view, the hierarchy, and the controller. Drawee view is a subclass of Android view, and we use it to pass the events to the controller and to tell the hierarchy when to draw. Drawee hierarchy is a passive component, basically just a composition of drawables that represents the image on the screen. And finally, Drawee controller is a component that, based on those events, submits the image requests and controls the hierarchy. Here we see an example hierarchy that, as its root, has a fade drawable. There are three branches: one for the placeholder image, one for the failure image, and one for the actual image. Each branch has its own scale type drawable, so that each can be displayed with a different scale type. A hierarchy like this allows us to display the placeholder image until the actual image is ready, and then once the actual image is ready, we can nicely fade to it. We use drawables rather than views because drawables are much lighter and also more flexible. Features. There are many features Drawee provides, and I'll just mention a few of them. For example, rounded corners is a commonly used feature that is surprisingly hard to get right on Android. Then sometimes we might want to display a low-quality image until the final image is ready, and to do that, we just need to specify those two URIs, and Drawee will do the rest for us. And finally, as we've seen earlier, we might want to use different scale type for the placeholder image than for the actual image. And all those things and many more Drawee provides out of the box. So some of the improvements over the existing solutions include simpler API, smarter resource management, a richer feature set, and smaller memory footprint. Okay, let's now see how to use Drawee in the app. Much like we would add an Android's image view in XML, we just add our Drawee view. And here we can specify various options, such as placeholder image, rounded corners, etc. And in Java, we just get that view and send the URI to it. If we need something more complex, we can build a Drawee controller instead and set that instead of setting the URI. All right, let's now talk about performance. Some of the performance benefits of Fresco are efficient memory management. For example, we make extensive use of pooling, and most of our memory-demanding structures live on the native heap, hence avoiding allocations and garbage collections. And then there is no duplicate work. For example, if 2 image requests simultaneously attempt to download the same image, only one network fetch is going to be performed. And some of the improvements we've seen comparing to the old pipeline views before include 65% reduction in photos load time. And here we can see Facebook for Android version 11 on the left and version 28 on the right, newsfeed scrolling. And as we can see, images tend to load much faster in the newer version, and we see a lot less gray boxes. To put this perf win in absolute terms, comparing to the old pipeline, Fresco saves over a century a day of human time waiting on photos for Android, on Facebook for Android to load. And this is pretty much all I have about Fresco. There is just one more thing. We thought it would be cool to share this library with all of you. So as of today, you can find it open source on GitHub. Thank you.
Thank you very much, team. So we will be starting off again in this room with our next session, which is around our data infrastructure. If you've ever wondered what happens on the other side of these networks, then please come along, because that's going to be a fantastic deep dive. We will be starting at 3:30, and we will have a dev infra session after that at 4:30. We hope to see you back for both of those. Thank you.